Welcome back everyone. In our previous session, we talked about k-means clustering, and we also talked about the elbow method in the previous session. In this session, I'm going to talk about an alternative to the elbow method, which is called the silhouette analysis. Now, what exactly is the silhouette analysis? It's probably best to just tackle it from the perspective of the formula that's provided here. You have P minus Q divided by the maximum of P or Q. So you have two things that's on the numerator here, which is the top above the top line. P is actually the mean distance to the points in the nearest cluster that the data point is not part of, whereby Q is the mean intra-cluster distance to all the points in its own cluster. Again, I'm going to just plot this out just to help you visualize this a little bit. It's always easier to have some pictures. So let's just say we have these clusters on this side here, and I'm going to choose a slightly different color here. Let's just use green, which is this one here. Okay, and next thing is I do need to plot a centroid. Let's just put the centroid over here, and also another one. Let's pick another color. That's purple color here. Okay. All right. So now that we've done that, let's take this apart. You have P, the mean distance to the points in the nearest clusters that the data point is not part of. So you have, basically you actually draw lots and lots of line, but for illustration purpose, I'm just going to plot the middle of the centroid here to the middle of this centroid here. So that this is really P. Okay, or P is probably better here rather than writing on the line itself. Okay, let's change the color a little bit. Let's change it to dark blue. Okay, blue, probably not a good idea. What color can we choose that's distinctive? Let's just choose green. Right, Q here is the mean intra-cluster. So intra-cluster basically means that it's within the actual cluster. Okay, so intra basically means within. Okay, to the points in its own clusters. So this is means here, so you have measurement from here to here, here to here, here to here. So basically you have a whole lot of measurements depending on how many points there is. So we have x1, and then you have x2, and then x3, and then on it goes. And what you're doing here is that you're finding the mean of all of these, so divided by n. Right, what can you actually get out of looking at that? First thing, the top part here basically is contrasting two things. Your inter, this one is inter, and Q here is intra. Okay, so you're trying to maximize P and you're trying to minimize Q so that the top number is as big as possible. That's really the basic intuition that you can draw out of this. The maximum here is just basically standardizing it. So it's picking the largest number possible, either P or Q, so that this here is as close as possible to 1. So let's just read this different interpretation. The score range between -1 and 1. When it's close to 1, it indicates that the data point is very similar to other data points in the cluster. A score close to -1 indicates the data point is not similar to the data points in its own clusters. So that therein lies the actual key point here, is that you have 1, all right, which is very similar to the other data points in the cluster. -1, meaning that it is not similar to the points in its own clusters. So what you really want to achieve is as close to 1 as possible. When you have -1, what you are really doing is actually you are lumping clusters or observations that is not meant to be together. You are lumping them together. All right, so as long as the number is closer to -1, you have heterogeneous, okay, observations or samples. As long as it's closer to 1, then what you have is it's getting more homogeneous. I hope that is useful. So let's do some coding to see if we can actually use this method to apply to our problem. Okay, So let's, from scikit-learn, again, we have a matrix. We're going to import silhouette. You can probably see why I actually make use of scikit-learn now, and you notice that it has a lot of really useful function that's built in. It really shortened a lot of the so-called time that you actually have to work with in terms of getting to the bottom of this. So I'm just going to continue with my notation. Sums of squares of error, but underscore is equal to an empty list to begin with. So we're going to use 4. K in range 2 onwards to, let's just say, 15. Actually use 8. We already done that exercise, so we kind of know what it roughly should be. K-mean is equal to K-means, and we're going to number of clusters is equal to K. Immediately we fit the X, and we're going to have SSE underscore append all of these value. We're going to append K, and we're going to append the silhouette score X, and also K-means dot labels. Okay, so let's run that, and now let's plot that. Okay, I'm just way too lazy to type it all out, so let's just copy this, save time, and plot that out. Okay, right. Couple observations that you can see here. Notice that there is the peak here. This is the point that is actually closest to 1. And so, based on the silhouette analysis, it's actually telling us that 4 is the best, followed by 5, followed by 3, which gives us actually a very similar conclusion to the elbow method, 3, 4, and 5. But the one thing good about the silhouette analysis is that it gives you kind of a ranking. Okay, in a sense, if you just purely take on the largest number, then 4 would be your ideal spot. Okay, so that would be the ideal part here. So with that, that will really be the end of this lesson on this clustering or unsupervised method using the silhouette analysis. In the next session, I'm going to show you another different one. We've covered elbow method, the elbow method. We covered silhouette. The next one we're going to go into is called the mean shift method. So I look forward to seeing you in the next lesson. Thank you for watching.